He's held various positions at Corning, all related to exhaust systems. His current role is Regional Technology Manager EU, responsible for supporting technology and product support for new applications for the light duty, heavy duty and non-road customers. Please join me in welcoming Dominik.
Thanks, Nick. Good morning, everyone. Title of my presentation is around alternatives to the diesel, also address diesel aftertreatment, but alternative fuels we discussed yesterday and going to discuss today. Also want to take the opportunity to quickly introduce Corning for those who don't know Corning. Corning is an American-based company, pretty old, founded in 1851. We had last year around 48,000 employees. So we do more than only aftertreatment. We have various areas of divisions, so to say, but we are all, it's all around material science. So glass and ceramics is our key business. Corning's pretty proud of its track record of innovations. One for us relevant is the invention of the substrate for catalytic converters. The first extruded catalyst was invented by Corning. We celebrated it 3 years ago. There was that 50th anniversary. Very important for us is optical fiber. Currently, AI data center rely heavily on Corning products. And then smartphones, we are leading the market for cover glass smartphones, LED, OLED glass, and so on. So this is the segments where Corning is very active. But for today, we're going to talk about non-road machinery. I want to share my thought on the challenges of decarbonization. I want to show our view on different architectures for different fuels like gas engines, hydrogen engines, and want to talk a little bit about substrates and filters. You just saw in the previous presentation how important filter design is and how it impacts performance. This gets even more important if we get stricter regulations maybe. I want to show then 2 examples from a recent publication. We had something at SAE, a DOC on filter. Interesting maybe because it could be more compact than DOC and DPF separated. And then there is, we recently did a study on natural gas applications on highway, but in case this becomes important for off-highway, we looked into the impact from CPSI, cells per square inch, for those who don't know the acronym, so basically the number of cells a catalytic converter has. And then I'm going to summarize. Mentioning the challenges, I share many of those that were discussed yesterday. So there is the operational challenges. So permanent high power density need draws a battery empty pretty soon. Multi-shift operations is a big challenge for electrification. Downtime like swapping a battery package versus refueling versus charging. Then the complexity of duty cycles, space constraints, and so on. From an energy supply, we discussed a lot yesterday. The issue we don't get electrical grid to all places, right? And high power fast charging, we learned yesterday in the Volvo talk, is not even available in rural applications. So there's a truck running around recharging the machines, which sounds like a big hassle to get this done. Economical barriers are very high. Non-road is cost sensitive like on-road, I guess, maybe in the same range. Batteries are still more expensive than aftertreatment. And fuel cost savings, of course, depend, like hydrogen price at the moment is super unattractive. I mean, in Germany, we have like 15 euros per kilogram. At the Hydrogen Alliance conference, they said we may get to 6 to 8 euros per kilogram once we have a high load factor, but this is in the future, like the e-fuel price. At the moment, it's the economical barriers for alternative fuels are very high, and then the landscape of subsidies, that's basically where we have to rely on our politicians, which is also a challenge. Looking into regulations, Johnson Matthey yesterday gave a nice outlook on how it could potentially look like. We put for the US a question mark behind Tier 5 due to the current administration, but of course we hope it's coming. For Europe, stage 6, I also put a question mark because the date of the introduction is unclear. We know the Commission is working on it. They're supposed to propose something, but the timing is uncertain. The expectation I share with Johnson Matthey, we will get PN10. We get a lower PN number, and after I've seen the Volvo presentation yesterday, I hope that we get lower limits also for the low power machines below 19 kilowatt, and that they get more stringent NOx and PM targets would be good for those cities who still allow combustion machines. On China, we see China 5 in 2030, and on India, TREM 5 for next year. This is a table I took from the internet. I think it's a good starting point to discuss fuel properties and groups of fuels that could be alternatives, starting with low sulfur diesel as a reference, and then there's biodiesel out in the market, and there's HVO in the market. HVO, you just hear very positive feedback. You just read good. The feedback is very good. It really is a drop-in for fossil diesel. CO2 potential is between 70-80%, I think. It requires hydrogen for the process. The biodiesel is also nothing new, available since a very long time, but is more tricky, I guess, than HVO. There, the devil is into the details for biodiesel. It's like the quality, and also biodiesel needs stabilizing agents that could be critical for some of the catalysts that are in an after-treatment system. But HVO is very uncritical, I hear, throughout the industry. Talking about gaseous hydrocarbons, not very widely used, I guess, for non-road machinery. In China, currently booming for on-road transportation, and also nothing new. There's available technology to address emissions from gas engines. And then the last in my list I want to discuss today is hydrogen, and we just saw it in the LIPER presentation. Hydrogen works. It is as a feasible solution as low carbon fuel or zero carbon fuel. Jumping into the architectures for different fuels, I focus here on stage 5 system above 56 kilowatts. Future system, I would agree with DNEX. There would be a pre-SCR basically needed, or to address a lower temperature DNOx, maybe even a catalyst heater could be needed to enable these 90% reduction in NOx for the next stage. But TBD, right? We saw catalyst heaters in Europe for Euro 7, but they disappeared again due to the legislation not enforcing them. HVO, as I said, equivalent to diesel for biodiesel, elevated NOx emissions due to the higher oxygen content of the fuel, leading to more NOx formation in the combustion chamber. This could be addressed by a machine dedicated to biodiesel. You could address this by, for example, more SCR volume, and to get more volume into the same space, you typically just increase the CPSI. Gaseous hydrocarbons, looking into a stoic engine, stoichiometric. In on-road, they are equipped with a three-way catalyst, one substrate versus a complex after-treatment for diesel. And then a filter is optional. We see filters in Europe already for Euro 6 in place, for buses and so on. They use filters, but the limits can be achieved also without filters. So it's up to the OEM to decide whether he needs a filter, because the emissions basically occur from oil combustion, more or less. The the low reactivity of methane is a problem for the catalyst companies. The light-off temperatures are significantly increased. There is PGM technology out there that addresses this, and I'll show you later that from a substrate, we as a substrate supplier can also help with higher CPSI, and higher means, let's say diesel, the base case is 400 CPSI as the best-selling substrate, but you can go higher, of course, for a three-way catalyst. And then lean gas engines require, of course, some sort of DeNOx aftertreatment. And the filter is optional. Now for hydrogen, so there's a little bit of hydrogen already on the market. There's Deutz JCB for non-road, Liebherr is testing, and MAN is selling a small fleet of trucks, I think a couple of hundred. So there is something on the market, and in Europe, I think Deutz is using a DPF architecture, similar to what Liebherr showed. MAN has, for on-road, came up with the SCR on filter system, no hydrogen slip cat, but the SCR-coated filter and a slip catalyst. And to address the DeNOx, the filter size is adjusted to have enough catalytic functionality on the filter. SCR on F offers, of course, here, if you optimize it for hydrogen utilization, offers the potential to have a more compact system versus the diesel system. You might free up some space for hydrogen tanks. This is the case can be the case for on-road and off-road applications. Now, the little bit details about filter technologies for now and for the future. So filters sounds easy, but for us it's rocket science. It's super complicated how to select the right filter, because you have many things. First, you need to select the material. At Corning, it's either cordierite or aluminum titanate. You see in brackets here, the difference is the density. They are both oxide ceramics, meaning they are fired under oxygen atmosphere. The microstructure it starts to get complicated because you can play around with porosity and microstructure in forms of mean pore size. And this gives you many, many combinations already of product design. To summarize or to simplify, a smaller mean pore size boosts filtration efficiency, higher porosity enables high permeability, saying low pressure drop. And we have products, you see that high porosity, we have aluminum titanate high porosity for SCR integration, we have cordierite filters for SCR integration, and we have conventional filters, conventional meaning for low amounts of wash coat or DOC integration. The middle diagram, cell design, yesterday we saw Texaco, it was about ash storage and maintenance, and purely by design you can increase your durability if you go from a 212 as reference here, and then you go to a 307 ACT design. ACT means asymmetric cell technology. You get more than 30% more inlet channel volume, and you can do modeling or very complicated simulations, but basically you just need to, it's a geometrical measure, is your inlet channel volume, and that describes the durability of for your ash. The bigger the inlet channel volume, the higher the durability, very simple. And the right one is the impact from cell design on thermal mass. So even if you use the same porosity and same material, based on the number of channels and web thickness, you get a different thermal mass. Now here the 212 has a higher thermal mass than the 307, meaning a 212 offers you more thermal robustness versus a 307. Of course, you can make this diagram now for any porosity, and then you get a different picture, but this illustrates you just that there's a trade-off in any direction, right? You change this, you get another change for another property. From filters, we use the same technologies and designs or similar designs for diesel, for gasoline, and so on. So it's surprisingly, they're all very similar filters for gas engines and for diesel engines, because a passive operated system has not a very strong requirement for thermal robustness, and the soot load is typically fairly low. Second is substrates. So substrates, I said 404 is a typical product used in diesel, but there's more products around. Like 206 is used in position 1 when you only want to have a certain conversion and a very low pressure drop. We have 305 as an alternative. And we have ultra thin wall products. If you need more catalytic performance, we go to 403, 603, 602, and all this is size dependent. The diagram with the bubbles shows you pressure drop on the y-axis and geometric surface area on the x-axis. And the diameter of the bubble is the so-called light-off factor. That's a simple correlation to emissions performance. While a lot of surface area, of course, enables you to have more catalyst, the smaller diameter of the high CPSI gives you better diffusion. So there's a better interaction between the exhaust and the catalyst on the substrate. That's and you will see that later on when I talk about the CNG results. But it's specifically if you're space constrained, higher CPSI is one way to get this more catalyst into the same package space. 2 example applications. DOC on filter is the first one. We had an SAE paper this year. I took 2 diagrams from this year's SAE paper. So you see the left diagram on the Y is PN filtration efficiency, on the X is soot load in grams per liter. So first of all, with soot, every filter filters super good, right? There's no issue. Soot is a super filtration enhancer. When you look at the 0 cross point of the diagram, you see that the blue filter, which is low mean pore size, is significantly better than the red filter's medium pore size. And in this diagram, which is very busy, you see there is DOC plus bare filter, there's DOC plus coated DPF, and there's DOC on filter. But it doesn't really change the picture of the filtration efficiency. A low mean pore size filter is better than a medium pore size. That's the conclusion of this diagram. Is this important for non-road? Yes, because even in a ramp mode cycle or in a steady state cycle, you run at maybe a high NOx to soot ratio, elevated temperature, you burn off your soot cake and you suddenly see soot slip. So a good base filter is also important for non-road, specifically if your engine is a non-EGR engine, very clean with high NOx to soot ratio, filter property is important. The right diagram is the impact on pressure drop, comparing again medium versus low mean pore size. The soot loaded, you see the low mean pore size filter has a little bit higher pressure drop, but it's not dramatic, and the highest penalty you have with the DOC on filter technology. In the study, the recent study we did at DOC on filter, we also looked into regeneration efficiency, and we looked into both cases, active and passive, and Mr. Pfeiffer explained it very nicely. Passive is by means of NO2, and active is by means of temperature. You see that the passive system, that's the top diagram on the left side, the coated filters, either if it's DOC or DOC on filter or DOC and coated DPF, they outperform the bare DPF, which is the red circles, the empty circle. Below, where you have active regen by means of hydrocarbon injection, the regen efficiency of the DOC on filter falls behind the other 2 versions. And the reason is shown in the right diagram. If you use hydrocarbons to increase your or to regenerate the filter, you need catalyst to boost the temperature, to convert, to create exotherm, And then at the inlet of the catalyst, the x-axis is the DPF length. There is no catalyst because you need first to move into the axial direction to get an exotherm. So for an actively regenerated system, a DOC-on filter has its disadvantages or challenges. But for passive regen, we think DOC-on filter is a feasible way to get to a more compact system. The last technical example I want to show here is impact from CPSI on conversion in a natural gas on-road example, 13-liter engine. All three configurations had the same PGM. You see this is an average of 3 repeats, that the 750 substrate showed higher bed temperature versus the other configurations, and that's an indication of better catalytic activity, leading to higher temperature, and higher temperature leads to higher conversion. So the methane slip is at no PGM cost optimized by using a high CPSI substrate or higher CPSI substrate. Yeah, so that's the end of my presentation. So the good news is we have products for the current legislation stages in case we see Tier 5, Stage 6. We have them already in the portfolio from a filtration I think we can address with our low pore size products. They will be ready for more stringent PN or PM regulations. On a catalytic converter side, there is higher CPSI can do the job. We not expect any new technologies required from our end. We have this ready for, develop this for Euro 7 on-road. We have everything in the portfolio. A little bit uncertainty on the heating thing, how to get the first SCR warm. I guess the regulation will be done in a way that catalytic heaters electrical are not needed. So again, I think we have everything already in our portfolio. I showed some results from DOC on filter, look promising, but there is a disadvantage really associated, which is the active regeneration. And then I just wanted to put your emphasis a little bit on, if you talk about substrates, keep in mind there's more than one substrate available. We have different technologies ready for you. Thanks.
Great. Time for questions. Who would like to go first? Any questions from the floor? I have one question about how many more stages of regulation is it conceivable to have before the exhausts are so clean that it becomes meaningless or cost prohibitive? Are we in an end game?
Yeah, that's a good question. I think with the for Europe, with the decarbonization targets, I think Euro 7 is the end game, and I would assume that the next stage in on-road legislation would be the last one at a certain achievement level of electrification. It does not make sense for air quality to further regulate the emissions of combustion engines. But I think what I learned yesterday was really these low power machines. I think they still have an impact on air quality. So there a new regulation is really needed, I guess. That's my personal opinion.
Thank you. Final questions, otherwise we'll press on. Yes.
So Matteo Longolive, Machine Build. The SAE paper you're showing with a different blend and the impact on the NOx, it's really interesting. This is based on which kind of certified biofuel, as US or Europe?
Which one?
Which kind of biofuel you consider for this paper?
Yeah.
And then if you have the same picture also for PM, different blend.
Yeah, no, on biodiesel it's very generic. So I think just the statements are made on literature statements that HVO has zero impact. In B100 there's a quality variation, I think, in B100, but we are not going into the details of per region where are the differences in the fuel properties. I think biodiesel had a boost during the Olympics in France, but it's very local, and I think the quality is really can vary from country to country, from feedstock to feedstock. But we didn't look into that detail of properties per country on biodiesel.